College Dublin. He's a well-known name again in the power systems. He studied the optimization and economic aspects of power system as well as stability of large interconnected network. Maybe I didn't put that the best way. But
no, it's fine. Thank you. Thanks very much for the introduction.
okay, so please.
Is there audio? Okay.
Just wait a minute. We need to open. We need to begin the recording. Okay. Yeah, it's fine.
Okay. So I've been asked over the couple of days a few questions about Ireland, so I thought I would give a bit of an introduction about Ireland and some of the things that are happening, and perhaps the contrast with GB. So Ireland's like the 10th side of the GB system, but very similar issues and problems and solutions, hopefully, as well. So that's sort of a brief overview what I want to talk about. So Ireland is looking to achieve 80% renewables by 2030. So I want to talk about some of the issues that introduces. Whenever I speak, I'll probably use the word I and we quite a lot. What I really mean is the various people listed at the bottom, they're the people that actually did things. So I'm really just presenting on their behalf. So whenever I use I and we, it's just being maybe lazy. It's really them that did everything. So just a very high level overview of the Irish grid. So peak demand of about 7 gigawatts. So roughly about, let's say, about the 10th the size of the GB system. It's a dual currency system. It uses the pound and also it uses the euro. There are a couple of high voltage DC links with Great Britain. It's gradually looking at higher shares of renewables, so a lot of wind generation on the system. So you can see roughly 6 gigawatts wind. Solar is gradually gearing. Last year wasn't too windy. The wind contributed about a third of the demand. But at certain times, particularly at night, wind has contributed a very high share of the demand. So the peak for Northern Ireland is 154%, for the Republic of Ireland, 98%, and at certain times combined, it has been 100% of the demand has come from wind energy. And there's also very importantly, a stability limit in terms of how much non-synchronous generation can instantaneously be allowed online, whether that's from wind, solar, or HVDC. And that's currently set at 75%. So just a high-level map. The map on the left is looking at the demand locations. So a lot of the demand is on the east of the country. So this is Dublin here, we have load center. And then the map on the right is looking at the generation locations. So the yellowish circles and the black circles are your conventional generation, your gas, coal, and then the green circles are looking at wind turbines. And if you look closely, there's one small offshore wind farm here. Basically the first offshore wind farm in Europe, but other countries across Europe have sort of rapidly overtaken Ireland in that scope. So GB, we heard that there's a north-south problem. Lots of wind generation in the north, lots of load in the south. In Ireland's case, it's an east-west problem. So potentially lots of wind in the west of the country, lots of load in the east. And again, we've got similar problems, how you get the generation where the loads are. Looking forward to 2030, we're looking at 80% renewables, lots of AVs, lots of heat pumps, so on. And you look at my graph at the bottom showing 2020, doesn't look too bad in terms of wind and solar. And then you look at the ambition for 2030. And again, the same question that was asked about GB, is this actually achievable, given that there's only 6 or 7 years left? And yes, you are seeing correctly, yes, there is that much solar PV predicted for the Irish system. It may not be that sunny, but there's very high ambitions for solar generation. So a lot of solar is expected, a lot of offshore wind. So whenever I draw my maps, they look very different. So on the demand side, there's a lot more electrification of heat and transport. A lot of the data centers really won't be in Dublin, so it accentuates that load problem. And you can see that there are large plans for offshore wind and also for solar. And there's also a lot more interconnection. This is just going back to my 2020, this is where we are roughly. This is where we want to be. So, and we've only got 6 years, 7 years left. Looking slightly longer timescales, if you actually look at the maritime area for Ireland, it is this sort of red region here, which is much bigger than Ireland itself. So the ambition is that there will be offshore wind farms in the Atlantic. It might be that they're directly connected to the electrical grid in Ireland, or it might be that we convert that wind energy into hydrogen or ammonia or something like that. And so in the right-hand picture, you can see of Ireland interconnecting with the main European grid and essentially being a renewable energy exporter, where the renewable energy resource is much, much bigger than what Ireland actually needs. At the same time, if I look at the demand, and this is split the demand into various sectors, and the bottom ones are residential, commercial, industrial, and they are relatively flat predictions for the next 10 years or so. Where we're seeing a lot of, or where we anticipate a lot of change is, first of all, in the blue columns, which is electrification of heat transport. And you can see also the yellow in terms of data centers. So in most countries around the world, they might talk about 2%, 3%, 5% of their demand coming from data centers. In Ireland, the projection is that it might be as high as 30% by 2030. So a very, very large share of the demand coming from data centers. And of course, as you increase the demand and you're looking at 80% renewables targets, that also implies that you need to build more renewables to keep your percentages in mind. So various problems that introduces. So here I'm plotting on the x-axis, the share of wind plus PV against demand. And you can note that my scale goes from 0 up to 300%. So certain times, the available wind and PV might exceed the demand by a factor of 3. And then here is the cumulative probability. So there's going to be certain times whenever you've got far too much wind and solar, greatly exceeds the demand. What do you do with it? And at the other end, you're going to be down here where it's not windy, not sunny. How do you supply the demand? And I mentioned my stability limit as well. So at the moment, there's a limit of 75%. So if we look at our axes, we can see that if we keep that limit, then for about 50% of the time, we've got too much wind and solar for the system. You can also see for 2030, there's a target to get that up to 95%. So essentially, you're just operating the system with wind and PV, and almost all of the conventional generation has been switched on. So I've drawn this for the 100% case, and that only improves things slightly. There's still going to be 40% of the time whenever you've got too much wind and solar. So there are stability issues in terms of can you actually operate the system with just wind and solar? And even if you say yes to that question, you've still got major imbalance problems. So initially, I'm just going to look at this end of the curve, which is what do you do if it's not windy and it's not sunny, and how often does that happen, and how long is it likely to last for? So the Germans have invented a term for this, which is called Dunkelflaut, which you might have heard of, which essentially means dark doldrums. So days when it's not windy and it's dark. And this is sort of counting the number of times a year when you mightn't have much wind and solar on the system, and how long do those events last. And really what you're concerned about is the extreme events when it's not windy or something for a long time. Yes, you might have some storage that you can use. You might be able to use your interconnectors, but what if your neighbors are facing the same issues? So you can see we might expect 3 or 4 days once a year when you don't have wind and solar. And the concern is, what about the extremes? What about the 1 in 10-year event, the 1 in 20-year event? What will they look like? So one of the things that we've looked at is the impact of climate change. So looking towards the end of the century and creating sort of numerical weather prediction models and see what will the climate look like then. So the various columns that you're seeing here are different weather models, different predictions of what might happen the temperature. And you can see that they're not all the same, they disagree. So the black rectangles that you can see are essentially the mean value. So the expected where we might end up. And so what we're seeing here is this is plotted against sort of a typical wind power curve. So we're seeing that during the winter time, it will probably be more windy. So turbines will be operating at their maximum output more of the time. And during the summertime, it will actually be less windy. So the times whenever the wind turbines are operating at a low output will increase. The times when they're operating at a high output will actually decrease. So windier during the winter, less windy during the summer, which emphasizes the advantage of going for a PV system as well. So you can use all the wind in the summertime, all the wind in the wintertime, and then switch to the PV during the summertime. And this is quite a complicated graph, but it's splitting things up into onshore and offshore, and it's looking at sort of 2 forecast scenarios. So the blue one is perhaps the more realistic one. The red one is looking at sort of higher temperature increase. And it's sort of measuring what will happen in terms of how frequently events occur and how long they will occur. So there's 6 plots here. I'm going to focus on the winter ones because we're looking at wind here. And so you can see that for onshore, what we're saying is that there will probably be slightly fewer events and they'll be slightly shorter, which is good news. And similarly for offshore wind, there might be slightly more events and there'll be slightly longer duration, which is bad news. But you'll note that we're not actually deviating too much. So encouraging signs that climate change isn't going to make things too much worse, but it's really those extreme events that we're really concerned about that might mean that we're lacking wind and solar for several days. Okay, so looking at sort of more on the other end of the curve, whenever we do actually have a lot of wind and solar on the system. So reserve has been talked about earlier. There's a number of new reserve products being introduced. So fast frequency has been talked about for the last couple of days. Primary reserve, tertiary reserve, so on. The hope is to operate the system at up to 95% SNSP, system non-synchronous penetration. So essentially just wind and solar on the system. New plans for interconnection with France. That will actually increase the size of the largest in-feed. So that causes stability concerns. And if you have all of that wind and solar on the system, you begin to think about what about the conventional units? How many do you need? Where should they be in order to support the voltage and the fault level in the system? So at the minute, there's a requirement for at least 8 units to be online. The plan for 2030 is to reduce that to 4, maybe even 3 units. So operating a system with just 3 synchronous units on the system. And those generators should be distributed around the system. Grid forming was mentioned in the previous presentation. Again, today discussion stage. If you're a system operator, most important thing is that your system is secure. Academics can approach you and say grid forming is great, but if system security is paramount, you want to think carefully before you go down that route. So grid forming will come, but not in the immediate future. And things such as carbon capture and hydrogen, again, they're part of the future, but we might need to wait a few years. So I mentioned briefly reserve categories. So traditionally there would have been sort of 7 categories. As you add more wind and solar to the system, you're introducing increased variability, increased uncertainty. You want your system services to be faster, essentially. So a number of new faster services have been introduced. And also wind forecast uncertainty has been introduced. A question that was being asked earlier was what happens whenever there is a fault, and should you prioritize your active power recovery or your reactive power recovery? Most power systems around the world prioritize reactive power recovery, but this particular system service actually emphasizes active power recovery, so it's unusual. And it's because there's so much wind in the Irish system potentially, and it could be quite concentrated. So I'm just looking at a 2030 scenario and looking at adding various solutions, Seekers condensers, medium duration batteries, heat pumps, electric vehicles, data centers, and so on. And you might look at some of these numbers and say, I'm assuming that 60% of residential heat pumps will be demand responsive. And similarly, 60% of electric vehicles will be demand responsive. And you might say that's a very optimistic assumption. But spoiling my own results, whenever I get a couple of slides ahead, you will say to yourself, that isn't actually enough. That isn't actually sufficient given the renewables targets. So it's not just about building the wind turbines and building solar farms, actually making the system operate in a sensible manner is extremely challenging, and everything else needs to change along with it. So this is sort of looking at 2 variations of an 80% renewables target. Essentially, the top one is looking at a default portfolio, and this one is sort of linked with the Ukraine conflict, where the Irish government said that we actually want to re-emphasize our ambition towards renewables, and we want to build more wind and more solar. So essentially this solution, although the target is the same, there's actually more wind and solar included. And what I'm plotting here is the rotational inertia in megawatt seconds. And here I'm plotting time. So the blue curve is representing time measured across the year. And then the orange curve is sort of ranking everything by the inertia value. So at the minute, the minimum inertia on the Irish system has to be at least 23,000 megawatt seconds. In the future, that will reduce. So this is suggesting a minimum of maybe 15,000 megawatt seconds, because we're displacing conventional generation. We're operating with more variable renewables.
It's a horizontal axis.
Time. So this is 1 year. This is plotting hourly values.
The entire plot is 1 year.
Yes. Yes. So you can see it's very noisy. Generators getting switched on and off on a daily basis, on a weekly basis.
What is the yellow one, please?
The yellow is all of these blue points ranked in order.
Increasing rearrangement.
Yes. Yes. It's because the blue curve is what is going on. So how often am I actually sitting at 15,000? How much time am I actually sitting at 35,000 plus? And you can see in this case, whenever you add more wind and solar, you're able to displace more of the conventional generation, and you're sitting at lower levels. So doing something similar for the combined cycle gas turbines, we're counting the number of units. And you can see we might be as high as 14 units, which is even that is small for Great Britain, but we're going down to 4 units. And really those 4 units, they're not really there for energy, they're there for voltage support and synchronization and fault level and all of those stability issues, and they're being spread around the system. So it's really pushing the system to the edge. And the concerning thing is this is only an 80% renewables target. So in future years, the government will say, well, why not make it 90%? Why not make it 100%? And Ireland doesn't have any nuclear generation. So that makes it even more interesting. And then doing something similar for rate of change of frequency. So this is looking at if we lose a generator, how quickly will the frequency change? And as you add more wind and solar to the system and you displace your conventional generation, then but less inertia, the rate of change of frequency will be higher. So there's a limit of 1 hertz per second. So the system is dispatched to maintain that limit. And you can see as you add more renewables to the system, potentially you're operating closer to that limit. But across the year, you can see that the inertial level potentially can vary quite a lot, and the rate of change of frequency level can change quite a lot. So similar to GB, Ireland is looking at synchronous condensers as being part of that solution, at least in the short term. And so the synchronous condensers are providing inertia, they're providing fault level, they're providing voltage support, and they're doing it at 0 megawatts, which is important. So what you tend to find is that even though you give the freedom to the system optimization to use the synchronous condensers, it either tends to say, if it's not windy and it's not sunny, and hence I'm using my conventional generation, then I don't need the synchronous condensers. But if I do have a windy day or a sunny day, then I'm using all of the synchronous condensers so that I can displace my conventional generation. So if I look at my various flexibility measures, and gradually as we add more flexibility options, such as synchronous condensers and medium storage batteries and so on, you can see that I'm reducing my cost, which is what we hope to see. And similarly, as you might expect, the operational hours for your conventional power plant reduce, particularly as you add synchronous condensers. Synchronous condensers can provide many of the things that gas turbines can provide, apart from energy, of course. But synchronous condensers are extremely helpful. The thing that is concerning is the level of renewables curtailment. And you can see these figures are high. The problem? I get the cable. And giving you power systems to walk, and power system operators are always bidding for options. Yeah. Sorry about that. If I was a good system operator, I shouldn't have allowed that system to happen. I should have forecasted and set up sufficient reserve in my battery. But you can see that the curtailment levels are quite high, and then the business case arises for the developers. So what is happening in Ireland now with new contracts is that new wind farms are actually being paid based on their available energy. So not the energy that they actually deliver to the system, but their available energy. So it means that increasingly they don't have to worry about the curtailment. So the consumer is paying for the curtailed energy, even though it isn't actually being used by the system. Okay, so moving on to something different, which is looking at the network side of things. And
No.
okay, thank you. So one of the things that I mentioned earlier was that increasingly a lot of the wind generation is going to be in the west of the country. A lot of the load is on the east of the country. So you've got the problem of transporting energy from where it's generated to where it's needed. And increasingly, it is difficult to build new lines, or it can take a very long time to build new lines. So one of the things that we were looking at is, can we increase the utilization of the existing network and hence avoid the need for new lines? So there's a wide variety of methods that you can look at, from dynamic line rating to high temperature, low sag conductors and so on. I'm just going to focus on a couple of these, and in particular dynamic line rating, just because it's wind related. And if you're not familiar with the idea of dynamic line rating, typically an overhead line will have a rating which is based on assumptions on ambient temperature and wind speed, so on. And those tend to be designed for worst case conditions, so that the line rating will never be normally exceeded. And what you might do is have seasonal ratings. So you might say that during the summertime it's going to be warmer, so my line rating is going to be lower. But what you can then do as a next extension is do that in real time. So you can measure your local weather conditions and say, what if I updated things in real time? So if it was really windy, I can increase the rating. And if I've got a wind farm that is close to where that line is, then there's going to be a correlation between the wind farm output and the neighboring line. And one way of doing this is the direct approach, where you put lots of monitoring on your lines. That can be costly to achieve. So what we were looking at is an indirect method, where essentially you use sort of a numerical weather prediction models. And so it reduces your instrumentation needs. It reduces your need to access the lines and take the lines out of service, and so on. But the question is, will that numerical weather prediction model give you the same sort of accuracy as putting measurements on the lines? So what we've done here is to use an indirect approach and to compare the ratings that you might see against static ratings. So what I'm plotting here is the ratio of a dynamic rating to a static rating, and I've done it on a seasonal basis. So the red rectangles are representing the winter ratings. The yellow is representing sort of spring and autumn, and the green is representing the summer. And you can see that the intensity of color heading towards red is telling you that then it's more advantageous to have a dynamic rating. If the rating is blue, it's telling you it's still advantageous, but not as much. And what you see is that, yes, there is a variation, and you tend to find that whenever you're coming to the end of one particular season, you're seeing noticeable changes in color between, say, February and March, because you've changed your reference settings or your assumptions of what the temperature might be and what the wind speeds might be. But the seasonal ratings actually work quite well. Perhaps not as effective during the summertime, but they work quite well. And then here, doing something similar, and it's saying, what is the likelihood that you could achieve a 20% or a 0.2 per unit increase in your line rating? And again, you can see there's quite a seasonal variation. And perhaps a bit surprisingly, you're actually seeing the best advantage during the summertime. So it's not saying that you can increase your lines better in the summertime, but what it's saying is that the default assumptions are probably pretty good for the winter and maybe not quite so good for the summer. Or maybe it says something about the Irish weather, I'm not sure. So that initial map was just looking at data points around Ireland. What's obviously of interest is to do that same idea, but look at where the lines are, and also to look at the direction of the lines and look at the direction of the wind. And is the wind sort of normal to the lines, or is it parallel to the lines? Because that will have a major impact on the cooling that you can achieve. So whenever you overlay that complication, you tend to find that your ability to increase the rating is going to be reduced. So here's assuming a 0.2 per unit increase. If you're really optimistic and go for a 0.4 per unit increase, then not surprisingly, the likelihood of achieving that is going to reduce. So what we wanted to do was to assess this for the Irish power system. And what we wanted to do was think about what is the natural loading of individual lines, because you can say if it's windy here, yes, we can increase the rating, but at those particular times, is that line going to be heavily loaded? And you need to bring in a unit commitment phase here, because if it's a really windy day, then a lot of your conventional generation will be offline, and that will affect the power flows. If it isn't a windy day, then the conventional units will be on. They'll be in different locations, and that will affect the power flows as well. So it's not just where it's windy, it is what will the prevailing power flow and the level of power flow be in that location. So there's a lot of data. We simplified things. We tried to cluster the data. And initially we did this separately to create different clusters for solar inputs, dynamic line rating inputs, and wind inputs. The problem here is that whenever you do it separately, you get different regions, which becomes a bit cumbersome whenever you want to implement things. And some of these regions don't have smooth edges. So we modified things to try and make the edges smooth. And we also set things up so that the regions fit inside each other. So if you look at the northern region for solar power, you can see there's one large region. And then for dynamic line rating, we split that region in two. And similarly for wind power. So in some cases, we're splitting one region into sub-region. So it makes it a lot easier to implement. And I'm plotting the impacts. So Ireland doesn't use locational marginal pricing, but it's a good way of assessing the amount of congestion on the network. So if the locational price is high, it's telling you that your network is congested. So the red dots you can see on the east coast where the load is, you can see prices are high. The green dots where there's a lot more wind and perhaps not as much load, you can see that the prices are high. So this is the default situation where we have a problem. And once you add in dynamic line rating, you can see that you've got a lot of purple dots, which means that you are reducing the locational price, which essentially means that you are reducing the congestion on the system. So it's a way of sort of showing the effects of reducing congestion on the system. And you can also calculate market surplus. And again, this is from if this was a locational marginal pricing market, which Ireland isn't, but it's still a useful tool because it's telling you how much congestion there is and how expensive that is. And as you might expect, during the winter time, so January, February, December, you've got a lot more demand on the system, a lot more wind on the system. You're seeing a lot more congestion. During the summertime, not as much demand, not as much wind, a lot less congestion on the system. And similarly, you can convert this into sort of the impact of adding your dynamic line rating. So the UC is just sort of saying, let's dispatch the system and don't care about the network. I can easily dispatch things. And then the orange and green are essentially saying, we do need to recognize the network and we do want to recognize the impact of dynamic line rating. So you can see that the dispatch down or the curtailment is increasing. And again, we're talking about numbers that are in double figures. So curtailment is high given the very high renewable efficiency. And I'm taking a risk here and putting up some box whisker plots. So this is just showing different lines around the system, and it's plotting the line rating relative to sort of 1 per unit, where it's saying that on a seasonal basis, your line rating is changing. So 1 per unit isn't actually the same across the year. And there are particular lines, such as this one, where potentially dynamic line rating could be helpful because that line is going to be heavily utilized. So you can see that the extreme point is going up to 1.4 per unit. And we also did something similar for emergency operation. What if we have our intact network, then we lose a line? What will be the impact on the neighboring lines? It will tend to increase the loading. So if we consider an N-1 case, you can see that there are more lines where we're going beyond 1 per unit, and hence the advantages of a short-term overrating or dynamic line rating can be. And what we've also done, what I'm not showing here, is if you also add battery storage systems, if you add in power flow controllers, they can also help you to increase the utilization of your network. And you can see that the brown lines are essentially showing lines that have been sort of series compensated. The little tail days or squiggles are sort of showing dynamic line rating locations, and then the green and the red dots are showing the locations of batteries around the system. How are we for time?
Well, 5 months, 7 months, I don't know. How much would you like?
Not too much.
Yeah. If you stop early, you get denied.
No questions.
Yeah.
So this is the figure that I had earlier, and I want to focus on the yellow bit, which is the data centers. So as I say, in most countries around the world, they're looking at data centers, but they're only looking at maybe 3%, 5%. In Ireland, it might be 30%. So there's a lot of interest in saying that data centers need to help the system. They can't just be a burden on the system. They need to support the system. And if you look at a data center, you can sort of split it up into delay intolerant loads and delay tolerant loads. So delay intolerant loads are things that you cannot touch. That service has to be provided. And it's all the email and Instagram and everything else. You don't want to wait to have that service. But there are also delay tolerant jobs as well. And those potentially we can play around with. It might be that something needs to be done by 10 o'clock this evening. It doesn't really matter when it's done, so we can perhaps schedule that. So this is showing an example from a data server in Ireland. You might guess that it's sort of it's a Google server, might be something that gives it away. And this is sort of looking at a typical week and the sort of various inflexible loads that you might see. But what we're really interested in is the flexible bit. So what we're really interested in is playing around with the orange bit of the load, and can we shape this to help the system? So what we did was develop a very, very detailed model of a data server. And what I mean, so this is essentially a mechanical model. It's actually modeling all the rooms, all the walls. It's looking at the materials in the room. It's looking at the details of the air conditioning system. So it's not a typical thing that an electrical engineer is interested in. So essentially, this is coming from the mechanical engineering side of things. So it's a very detailed model of the building. And it includes all of the cooling facilities associated with the data servers and the control systems associated with the data server. So essentially, there's sort of two main types of cooling for data server. So on the left-hand side is the traditional cooling arrangement where you have a chiller. The chiller sends cool air into the data server cells and extracts or cools the air. What you can also do as well is that you can use outside air. So particularly during the winter time, you can use the cool air instead, and that's going to reduce your energy cost. So this gives you better temperature control, but this reduces the cost. The big downside of using something like Energy Plus is that it gives you very detailed models, but it runs extremely slowly. And for someone like me who's interested in, let's consider the Irish power system with lots of data centers. Running one data server is very slow. Running multiple data servers is it's not feasible. So what we ended up doing was developing sort of a multiple linear regression model of the standard data servers and the free cooling data servers to represent the wide range of conditions for different times of day, different seasons, and so on, with variations in ambient temperature. And this is the sort of thing that you might see. So the green dots are looking at the IT workload, and the blue curve is your standard cooling. And you can see that whenever the server loading is low, then they're comparable. But whenever the server loading is high, and hence the temperature is high, you're seeing large differences. So the free cooling is more effective in reducing those peaks, but ultimately the temperature control isn't quite as good. So we looked at a control system where we focused on the flexible loads, and essentially we gave the controllers a CO2 target. So we wanted to say to it, whatever the CO2 level for the system is high, in other words, it's sort of a conventional generation, no renewables, we want to try and reduce the demand and hence reduce the CO2 intensity. Whenever it is a windy day or a sunny day, the CO2 intensity is low, then we want to increase the data server consumption, or at least shift the load to those times. So I'm going to show a couple of variations. One where we're assuming that the data centers are fully flexible, which isn't realistic. The second one where we are focusing on the flexible load, but we're ignoring the temperature control. Again, it's not realistic, but what we're really interested in is the bottom one. We're focusing on the flexible loads and we're putting in temperature. So the reason we're putting in the first two is just to show the value of the modeling, that if you go for a simplistic approach, you will get an inaccurate or not useful answer. So this is a bit of a complicated graph to decipher, but essentially the red is showing me my predicted CO2 intensity for a 24-hour period. So you can see in the middle of the day, CO2 intensity is high. So probably it's not windy, it's not sunny. So what I would like to do is reduce my data server load that time. And similarly, at the end of the day, CO2 intensity is low. So that's when I would like to shift the loads to reduce the overall CO2 intensity across the day. So the black dots are showing my initial curve. And you can see as that I add flexibility controls, I'm able to reduce the data server consumption at the high CO2 intensity times, and I'm increasing it other times. So I'm shifting the load away from the, to say, high CO2 or high conventional generation periods and shifting it towards the low CO2 or the high renewables. And then this is just showing the operation of the individual data servers around the system. And each of them is doing their own thing. And then finally, this is just showing the temperature profiles across the system. So just to conclude, so Ireland achieved a 40% renewables target for 2020. It's now looking at 80%. Very difficult thing to achieve. I mentioned optimistic assumptions on flexible loads to help the system. They help, but they don't help enough. Location is very important. It's not just can you generate, but where are you located? Where can you help the system? So there are many solutions ahead, not much time to sort them out. And if we look further ahead, we're looking to get rid of all of conventional generation towards a totally wind and solar system. Hence things such as grid forming and so on very much come into the picture. Thank you.